everyone. From my side, so welcome and thank you all for coming. When we organized this conference, we were planning, I think the original estimate was 40 people and lots of time for discussions. We're now at 150 people and 10 minutes talk, and we apologize for that, but that was the only way to really cope with the number of people wanting to attend, which makes us very proud. There are some remainders of the original plan. One of them is this introduction talk. The other one is the 3-hour lunch breaks, which you should and can use to discuss science while watching the fishes swim under you. And there is a debate at the end, and I'll talk a bit more about that in just a minute. So the introduction is about, here's the title of the conference, the debate between local and global processes of the arts. This is not an IQ conference. I will know one of you go home and say this was an IQ conference. This is a science conference about different scales in galaxy formation. That is really what I want to take away from my talk. This is the message. There's a bit more. This is the main message. So why did we come up with this conference title? Sebastian said the excuse to come here is the Khalifa third data release. So I'll concentrate on some of the results we had that actually led to the title of the conference. To the left you see the stellar mass oxygen abundance relation, which is often called mass-Ellis relation, by Christie from Sloan data in 2004. And a lot of you know that plot, and a lot of you know the uncertainties associated to that. But the main point here is that to the right you see what we found from Khalifa, where we actually exchanged one of the axes. That's not stellar mass anymore, that is stellar mass surface density. So we turned a global relation, a relation that would concentrate all of the galaxy at one point, into a local relation, which means that it's valid and scaled, in our case, a scale of 1 to the parsec. And when we saw that, we thought that was very interesting, and maybe that means something. And some people jumped and said, yeah, so the local relation must be first, but I think it's really a chicken and egg question. Because as I'll show you that, I can't use data point as a Daltonian, so I'll have to walk over. If the outskirt of the galaxy was here, and your center was here, you would not end up here, you would end up here. Okay. So just summing up, all of the local relations doesn't necessarily give you a global relation, particularly when it's not linear. So the chicken and egg question is really up there. What causes those relations to look exactly the same? Some of the things we learned with Khalifa is a quote from Brock Kennicott, I'm not old enough to see things we discovered the third time. And so we thought it would be appropriate to remind us that, for example, this paper by Ryder et al., this has been all foreseen. Okay? So there is surface brightness oxygen relation, which was published 20 years ago. So, but of course, the quality of the Khalifa data, just because it's better instrumentation, is much better. There are many more local relations. This is one that was published by Atlas 3D by Nick Scott, and what you see here is the escape velocity. So that's a measure of the depth of the potential versus observation quantities, so absorption line equivalent with it. And clearly there's a correlation, what means I have no idea. And I don't think we know, but it's very interesting that there are these correlations on very local scales, which may mean that galaxies don't evolve as points, they don't evolve as an entire entity, they rather, every part of the galaxy evolves independently, and then everything sums up. There are many more of those. There's the left part, many of you know, and this is just one of the plots, but there's many plots in different dimensions of the galaxy mass with the star formation rate, and there's a so-called main sequence, and we're missing a lot of galaxies here, those that are not form stars. But the interesting part is here that, again, you can do the same thing. You can do star formation rate versus stellar mass surface density. The same correlation exists with very similar scatter. You can play with tricks, and that's a bit far-fetched, but it's funny. You can look at luminosity, which would be something like mass, and color, which would be something like age, so color magnitude derivative of galaxies. And you can use a Khalifa result, which would plot surface mass density versus age, and you find again the same thing on local scales. So that really prompted us to start thinking, maybe one of the things that we're learning right now, as we have better spatial resolution on galaxies, is that there is really, it's not clear right now, and that is a chicken and egg question that I think we have to solve to understand galaxy evolution. There are more local relations. This one is metallicity versus IMF indicator. So really dwarf to giant ratio, and you can see there's a clear correlation on the left-hand plot, which is from Khalifa. trying to cite a bit of literature just to show that this is not a clear result. It's really out there in the literature for everyone. It's just that I happen to know likely. And it's something, you could have raised a hand, and Stefan would have done so if he wasn't the chair, that this is all well known because we know that the star formation law holds in many, many different scales. And this is a plot that is 10 years in advance of the other ones because it actually plots galaxies and molecular clouds onto one relation. Okay, so I don't have to show two plots. I can show the local and the global relation on the same plot. Y-axis is star formation rate, surface density, x-axis is stellar mass divided by freefall. So that is a way to put all of these into one relation and then to maybe gain physical insight. This is all great, and what do we make of this? Well, as Sebastian said, there is conference out of this. Can we do more? And can we use it to understand galaxy evolution? Two questions can arise, and I warn you, these go in order of increasing naivety or controlled stupidity. So let's see. But maybe they can spur some discussion. Maybe they can help us use our 3 hours of lunchtime break. First one, what is the right scale? Maybe 10 or 20 years ago, we would have looked at galaxies as points. So a galaxy is the entity we study, so it's a point. So it has a property, it's stellar mass, it's star formation rate. Now the plots I showed you on 1 kiloparsec scale, that has a reason. The reason is fortuitously that both for observations and simulations, we have large samples of galaxies on 1 kiloparsec scale. That is by chance. That doesn't mean at all that this is the fundamental scale. The fundamental scale can be very different. It can be very different from processes. And just finding out what scales are the ones where local goes to global would be very worthwhile. That would be very, very interesting. And that is something that I think we should look towards. And one of the things that can make us very hopeful is that instruments like James Webb and the extremely large telescopes will allow us to go to much smaller scales. Someone predicted that the poster would start falling down. A question that I ask myself, and I'm telling you this is going to be increasing philosophical stupidity, is this emergence? And so I looked up the definition of emergence. The emergence is the rising of novel and coherent structures, patterns, and properties during the process of self-organization in complex systems. That is a definition that I found on Wikipedia. Where else? And that really, for an astronomer, produces the thought of analytical expressions. Okay, can we express things that when you jump the scale and you start forgetting about the low-level physics and come up with the star formation law or something else? Most of what I showed you is not emergence because there's no jump in physical scale. There is a difference in physical scale, but it's not self-organizing. Okay, you have a locus metallicity, so a mass surface density that is not sufficiently different probably to be the same as emergence. But the other definition of emergence I found was that it doesn't have the word emergency, but the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. And this is a bit interesting because it leads to the question of what is the right level of complexity in our thoughts on galaxies. So Walcher just this year wrote this sentence down, and probably many people will subscribe to it. Highly complex and nonlinear physical processes involved in galaxy formation mean that numerical simulations would be a very good way to address the theory. But the question then arises, what is the right level of complexity? If you had a computer, if you had a software, if everything was perfect, you could re-simulate the universe atom by atom, you would have probably learned nothing. So there must be a scale between now and simulating the universe, something in between, where we would actually learn something. And what is that, and what does it look like? That is a big open question that will be very interesting to address. Maybe, as I said, increasing level of stupidity. Maybe give you my viewpoint, how progress in galaxy evolution can be achieved. I think simulations are not there to reproduce the universe. That is a wrong way to think about it. I think simulations are there to help us identify analytical laws. Okay? If you can make use of the simulation to understand where emergence occurs, then you can write down galaxy evolution in analytical equations. And really, I'm contradicting Walcher and Torsten and Klaus and whoever else in the room on this, and I do that on purpose. Maybe we can discuss it further during the week. But I'm equally critical of observations. When we started Khalifa, we knew that we would have 600 galaxies in the end, and we started off studying our pet objects. Someone went for mergers, the other went for early types of probability of the same thing. I don't think we should study pet objects. We should really use our observation capability to understand processes, because that is what matters. That is what really matters. Pinning down, as people who do semantic models call it, the parameters, trying to pin down the parameters from first principles will be much more useful. And finally, I think, and I'm not going to do this because I'm very, very bad at math, but I think we need a revival of analytic formulations of astrophysical processes. And maybe I'm wrong. I hope this is a good reason to discuss more. And you can come to me and anyone and start discussing. And it really leads to the thing on Friday, where we have a debate on the topic of what does it mean to understand galaxy evolution. And some people will say, well, we put the universe in the box, and that is how we understand galaxy evolution. Others will say, well, I want you to tell the story in words. Maybe that's much better. So what is it? 4 people have volunteered for that. They will get 7 minutes Friday evening, last day of the conference. They are allowed to show 3 slides, and you are supposed to discuss afterwards. The people are Barbara, Patricia, Klaus, and Vladimir. And if you want to talk with them during the week, they have agreed to being available. And maybe you can put thoughts into their talks, or maybe you can prepare your own questions for after the debate. And with this, I hope that we will all have a scientifically very productive conference, and thank you all very much for that.
Thanks for this very illuminating introduction. Before perhaps we open the floor for questions, I'm not sure how appropriate it is given the global nature. I'm going to put you on the spot a little bit, perhaps in preparation for the debate, and for us to keep thinking about specific questions, putting you on the spot, what would you think are the 3 major questions that we ought to address repeatedly at this workshop, and for which we need to have some sort of conclusion at the end? What would be the 3 global encapsulating questions that we ought to debate at this workshop? Or actually, it is a tough. Whoops. I may open the floor actually to everyone.
I'll draw on the Khalifa experience. I'm sorry. I'm the project scientist at Khalifa. So when we started Khalifa, I made a talk, and it had about 20 topics we absolutely needed to address, and that didn't work. And what came up was surprising. It was different from what I expected. It was much more interesting. So I will not mention to answer your question, but I will rather ask ourselves to try and maybe answer the question by the end of the week.
Well, Chairman Royce, I think it'd be nice to open the floor. Perhaps either you have comments vis-a-vis my suggestion, or perhaps some of the points that
feedback, star formation.
Anyone? Glenn, you have a great smile on your face. What would be the one question you think we should address at this workshop? And perhaps pass the microphone to Glenn over here.
And if you don't have an answer, you actually don't.
So maybe we should ask the chair first to actually do the first one.
This will be part. I will address an issue that many of us, I'm sure, think about when we write our papers and try to come up with the next awesome paper that'll, solve all the problems. It's either trying to refine a specific model or think about the philosophy of what we're doing. And at any given time, when we have a particular diagram, and perhaps this holds for everyone who will give a talk here, not just say, hey, I refined, I reduced the scatter by this, I changed the slope by that, oh, a few points disappear, but asking ourselves, what are the guiding physical principles that explain the slope, scatter, and 0 point of any relation that you show? All of your talk, if you can do that, when you show a plot, a figure, and you can explain, to start with, there's other questions, but you ask me for one, if for every major plot that you show, you can explain the origin and the physical principles that control slope, scatter, and 0 point, I'll be very happy. That's my suggestion. Anyone else for comments?
This is more comment about that. And please bear in mind that some relations are not power laws, please.
Sure, that's a good point. Whether just in log-log space or linear space, it doesn't need to be a log-log. The question is, how do you address, the distribution of points that you have, rather than saying, oh, it changes like this or like that. Let's aim for physical principles rather than specific technical reasons for those variations. Daniel, Thomas,
I think we should do something very different.
okay.
Whatever relationships we find, we should try to reproduce them in galaxy formation simulations. I worry, and it's my own approach, but I worry that we are too phenomenological when we interpret observations. We speculate scenarios and we think to understand stuff, but when we try to simulate it, it turns out we can't. And that's actually where really we understand the universe. So I think we should try to work much closer, not speculating over data, but to actually run simulations that explain them, and then give the answers in the same.
Right. Okay, so I would say that these two views are in fact complementary rather than orthogonal.
Can I just answer Daniel's question for a second? Daniel, you said that we should reproduce, or on the one hand you said we should try to reproduce counts, on the other hand you said that we can't. I think the part that we can is the one that we need to emphasize, because that is where we're learning. In a lot of simulations, people write, well, I'm reproducing this and this and this and this and this, and therefore I understand, but you don't until, I think the simulations don't reproduce the universe. They help us understand what we don't reproduce it yet. That is much more interesting than finding it.
All right, we're warming up. This is good. Jesus here.
Yeah, actually, I'm going to pose a question that I'm sure that we're not going to answer at the end. But it's basically what drives and controls star formation. Because that's actually what connects the micro and the macro properties. And even in simulations, we put recipes and stuff, but we really do not know what the physics is there. So I think that that's the largest and most important reason.
Okay. Okay, Vladimir Avila.
I think an important question is if galaxies keep memory of initial conditions, if the galaxy evolution keeps memory of initial conditions, or the internal physical processes erase these initial conditions. So this is for the big picture. We have to know if the galaxy evolution is driven by the initial conditions, by the cosmological initial conditions, or the internal physical processes at the small scale, kiloparsec scale, erase completely this initial condition. So I think this is a key question.
This reminds me, actually, as the microphone is passed to you all, please state your name so that everyone appreciates who's making the comment. We still have a little bit of time. I'd like to ask Ravid to come to the front. Maybe one or two more comments. Okay, in the back, if you can pass the microphone.
So coming back to positions versus sector processes, I think that the question of not just initial positions on cosmological scale as when the galaxy is formed, but also in what kind of environment it is. So what the interplay between large-scale structure both on galaxy group and planetary scales is fundamental to understand it and how particularly second-order processes project onto galaxy evolution, which is then determined by the processes in the galaxy. So it's a picture with multiple scales that we need to understand.
Okay. And I believe, Sylvain, you... I'll pass the microphone.
I guess as one of the AGN Quasar representative, I think...
What's your name?
What is my name?
What is your name?
Oh, Sylvain Billon.
Okay.
It's important to also consider that there's a supermassive black hole in many of the massive galaxies that are going to be discussed, and it's important to know if they have any influence at all on what we'll be talking about in terms of galaxy evolution.
topic tomorrow, especially the hand in the back, and that'll be our last comment.
Dan McIntosh, a birthday boy. So, I think one of the most important processes that happen in galaxy evolution is quenching, and so is quenching mostly a global or local process? I would like to know that.
My talk was really meant for what I don't think quenching is a good word. It's really bad word. Because quenching is not a process. Quenching is the main process. There are many processes that do quench, and we should try to understand each one, and not quenching in general.
Well, how about quenching processes?
That is not the word Shane used.
Yeah.
I was trying to talk about it.
Okay.
Trying to be nice to birthday boy as well.
All right. Did you want to have the last word?
Well, no, I didn't.
Or? You do have the last word. Yes.
I'm Patricia Tisera. No, I was going to, in relation to the models and the observations. I'm really interested in trying to find other ways of confronting simulation with observation, because observation now are providing much more complete information to the information, and we are still using the same tools and averages and more or less the same statistics when comparing simulation with observations. And I think we should be doing much better in order to get more information from the observations and to run these observations and simulation in order to learn, all the things that we want to learn. We still, I'm searching for a better way to make this confrontation between observations and simulations.
And maybe you'll tell us about that in your talk. Okay, I think now is a good time to start, to write it in. I look for my son at some point.
Okay.